Today we're diving into an exploration of energy transfer and rotational dynamics using everyday objects. Our experiment investigates how potential energy from a falling suitcase transforms into the rotational kinetic energy of a door. We're using a 54-pound door that we know the radius of as our rotating system and analyzing how adding different masses in a bag attached to the handle at the furthest point from the hinge affects the amount of time and angle traveled arc length of the door's motion. So the suitcase is also measured. It's a known height. That's our initial potential energy. And we're just going to very gently tip it over, applying the minimum amount of force to get it past that tipping point. It's not going to strike the door. It's going to be in contact with the door and continue to fall and push. And the door is going to rotate. Using precise measurements of the door's initial and final angles, along with the time of motion, we can calculate the energy transfer efficiency of our system. We can figure out the door's moment of inertia, center of mass, angular motion, rotational kinetic energy, and yes. So, join us as we begin.
So we used Ayham's door, and we tried to calculate the torque, but it was difficult to calculate the force because we didn't have anything to give us the force directly. So we tried finding the acceleration. But it was hard to stay consistent with the force, and we tried using an app like the physics toolbox and use the data to calculate the acceleration and use the mass of the door to find the force, but it was all too complicated, so we ended up just reasoning where the torque would be most effective, and we found that it would be most effective near the doorknob, where it has a greater lever arm rather than the hinge, where the lever arm is a lot smaller. So that's our findings for the torque.
So our calculations, we did the initial energy is the potential energy of the suitcase, mgh. So we plugged in our values. We got a potential energy of 235 joules. So for our first trial, we used the arc length to find the angle, converted it to radians, divided it by the time, and got our angular velocity of 0.1247 radians per second. Our moment of inertia, we used 1/3 m angular velocity squared and got 10.5 kilograms times meter squared. So that would make our final rotational energy of the door 1/2 in a moment of inertia times angular velocity squared. So that comes out to 0.08 joules. 0.08 joules divided by the initial potential gravitational energy of the tipping suitcase is 235 joules. So, that comes out to an efficiency of 0.034%, which doesn't make a lot of sense So actually, the experimental setup was flawed. I thought, I don't want to make this into an impulse problem. I don't want to just have a collision that is brief, because in my intuitive head, I thought, less energy is going to be transferred that way. So I wanted the suitcase to stay in contact with the door for as long of the fall as possible, thinking that would transfer the most energy. But actually, if the suitcase were to fall and right before hitting the ground were to hit the door at that point, that's when the suitcase would be falling the fastest and would have the most of its mass actually, um, you know, how we did it, the center of mass is during the initial tipping is not even over the ground. The tipping it's in motion. Well, yeah, no, it would be over the surface of the ground, but um, the the thing is that is a lot of energy that's happening after this. So if the door is getting pushed after the suitcase has tilted a quarter of the way, and then the door proceeds to swing, all that energy of the 3/4 of the rest of the suitcase's fall to hit the ground, 3/4 of all that energy is not transferred to the door. The door is already swung away. So actually, uh, we did this experiment fundamentally wrong. But we would have to take impulse into account.
Good evening, Professor. So our experiment is going to be us tilting this bag in such a way that it's not going to fall, but it's on the verge of. And then when the experiment begins, we're going to be touching this bag as it slowly falls down. And whatever force is transferred from this door back to the door is going to move and stop at certain times, as we have marked over here. And then after the first experiment gets finished, we are going to add 2 books, both one of them being approximately 150 grams, so that's 300 grams added per experiment. I'm going to be depositing them in this bag and hanging this bag on the handle of the door, henceforth increasing the weight of the entire door by 300 grams per experiment slide. And that's pretty much we're going to use this line. As you can see here, we have measured where the door has stopped, and using this line, we're going to measure the total distance of where the door traveled per experiment and per take, and that's going to be our experiment for tonight. Hey Professor, so in the end where we were able to conclude that we tried making an experiment where we could somehow transfer the kinetic energy from the suitcase to it falling towards the door, and seeing if the energy could be transferred, if it would be, how long it would measure. What we did was we ended up stretching the entire cable out and marking where the door would stop, and we were able to use the distance in a way to help us find the force being used by the door. This was done through a lot of calculations by me, Claudia, and Billy, and to how long it would measure. This took a lot of time and effort. We even ended up paying for like a couple of subscriptions for a physics app, so so our phone could basically record how much distance is covered and everything. Obviously that didn't end up working, so as you could see in our conclusion, you saw what we ended up having to resort to, which I think for our part was pretty smart, and we were able to by just adding weights, we were able to see how much of a difference it made, as like the door slowly stopped going as further, and it like slowly reduced the distance it went. Yeah, I hope you like our project. This project was created by me, Ayham Imran, Claudia, and Billy. Just Billy. And yeah, thank you so much.